Oh boy, I remember seeing this problem back in Calculus 2, and it's a tough one. I know that there's a memorization trick that's taught where when you play with this formula a bit, you'll actually end up with something under the radical where you can just plug in a magic formula to get the answer. But in this video, I don't want to show you that because if you just cram all these formulas to memorize right before your exam, I guarantee you're going to forget them, and I've been there too. So by the end of this video, my hope is you actually will understand how to solve this without any memorization. And before I dive right in, let me introduce myself. I'm Dave, and I used to tutor students like you back in calculus when I was taking it in college. And I'm actually a software engineer who made a fun ninja math game you can check out in the description below for your iPhone and iPad. But let's go ahead and begin. The first thing I did here was I rewrote what's under the radical, because when I'm looking at 9x squared minus 16, the very first thing I always check for problems like this with the radical on the denominator is to say, hey, is this a difference of two squares? And surely enough, it is. And when you have a difference of two squares or a sum of two squares under a radical, you should always be thinking about trigonometric identities and trying to substitute one in, okay? Now, what I'm going to do here is I don't like that there's a 3 here in front of the x. So I'm going to go ahead and let u equal 3x. And then when I take the derivative of both sides, I will find that du equals 3 dx. And what's nice, though, is that even though we have this x on the denominator in the original integral, don't sweat it, because if you know that u equals 3x, you can substitute in for that x because we can just rewrite this as u over 3 equals x, right? So I'm going to go ahead and now substitute everything in. And by getting rid of that 3 that was in front of the x, we are now one step closer to having the radical have something that's u squared minus 4 squared, which ideally I want to get rid of this 4 right here too and make it a 1. But hang on to that thought for a second, because the first thing I notice immediately is I have a 1/3 on the numerator here and the denominator. So I'm going to go ahead and just cancel those out to simplify this integral a little bit more. That's going to leave us with another expression now. And going back to the idea we had, if we want to have a trigonometric substitution for this part here, we know that whether you're adding squares or subtracting them, any trigonometric identity you're dealing with, the constant's a 1, right? Not a 4 squared. So what I want to do now is I want to actually just pretend I'm just factoring out 4 squared, or basically 16, and you'll see what I'm going to mean. Now, I'm sure a lot of you are already rolling your eyes and you're thinking, hey, Dave, why don't you just do a substitution here for secant of theta? I could, but again, in this video, the goal is to teach you understanding and not memorization, in case you don't see it yet, right? But if you do see it, tell me in the comments below. So after rewriting this by factoring out the constant, you're going to have this under the radical now. It's pretty straightforward, right? Because we had a 1 in front of u squared. So if you factor out a 4 squared to undo that, you'll have this 1/4 squared here. And now what I'm going to do is I'm going to go ahead and simplify that further by remembering that because I had a constant under the radical, I can actually split up the radical into a product of two separate ones here. And this square root of 4 squared is nice because I can just bring out a 1/4 altogether from the integral, leaving us now with this expression on the denominator. But again, I don't have a 1 in front of this u term. I've got this 1/4, right? But you know what's cool about that is we can actually stop right here and do a u substitution anyhow, because this -1 here looks exactly like how we want it to look. But why don't I just let this whole u over 4 be my substitution? I'm going to let u over 4 equal secant of theta. And then I can rewrite this to basically say that u equals 4 secant of theta, right? So that when I take the derivative of both sides, when we substitute in for du on the numerator, it'll be 4 secant theta tangent theta d theta, giving us this new integral. Aha, that's kind of cool too, right? Because now I can just ninja chop all these terms that are similar. And that's going to simplify things really nicely, because we'll end up with this new integral down here, where on the top we just have this silly looking tangent theta d theta. And then on the bottom, we know from our identities that secant squared theta minus 1 is the same as tangent squared theta. And that's going to allow us to ninja kick this even further and simplify terms more. And if you don't see that identity, that's okay. Just start with the common one, sine squared theta plus cosine squared theta equals 1. And you can divide every term by a trig function to actually derive this. Try it out. Now what I'm going to end up with is going to be tangent squared theta under the radical here. And that's going to just have a square root that cancels the power, right? So when you have tangent theta, d theta over tangent of theta now, you're just going to be having 1/4 times the integral of the differential d theta here, which is super simple. That just gives you 1/4 theta, right? Well, not so fast, because we need to also remember the original problem was in terms of x. But we didn't actually prove or show yet what theta is. However, we did have this substitution from before, remember? U equals 4 secant of theta. So if we divide both sides by 4 and take the arcsecant of both sides to cancel it out on the right, we now have what we can substitute in for theta, giving us this new expression, 1/4 arcsecant of u over 4. And then finally, we have to undo the first u substitution we did from the beginning, where we let u equal 3x, right? So when you put that back in here, you get this final answer, and you